Greetings and welcome to lecture number 13 on the course Introduction to Fourier Analysis. On the previous lecture, we showed that the Fourier transform of a Schwarz function is again a Schwarz function. The purpose of this lecture is to show that, in fact, all Schwarz functions arise in this way. All Schwarz functions are Fourier transforms of other Schwarz functions. We will prove this fact by an explicit formula, which is known as the Fourier inversion formula for Schwarz functions. This is the content of Theorem 3.9. Let phi be a Schwarz function and let x be a vector in Rd. Then phi of x equals the integral of the Fourier transform of phi at xi times e to the power 2 pi I xi dot x d xi. It follows that the arbitrary Schwarz function phi is the Fourier transform of the Schwarz function defined by xi maps to hat phi evaluated at minus xi. Note that this formula indeed defines a Schwarz function by the results of the previous lecture. As we already mentioned, the formula stated in Theorem 3.9 is known as the Fourier inversion formula for Schwarz functions. The second claim in Theorem 3.9 follows immediately from this formula. Indeed, by the formula, phi of x equals the integral of hat phi xi times e to the power 2 pi I xi dot x d xi. Then, after a change of variable from xi to minus xi, this integral can be rewritten as the integral over xi of hat phi at minus xi times e to the power minus 2 pi I xi dot x d xi. This second expression equals the Fourier transform of the Schwarz function xi maps to hat phi minus xi evaluated at x. This is exactly what the second part of Theorem 3.9 claimed. As you can already see, one often needs to deal with the function x maps to phi at minus x, so it is convenient to give it a special notation. We write tilde phi at x equals phi at minus x. With this notation, the Fourier inversion formula can be abbreviated in the following way. A Schwarz function phi equals the Fourier transform of the tilde version of the Fourier transform of phi. The proof of the Fourier inversion formula is essentially based on the observation that the Gaussian function is a fixed point for the Fourier transform. This is the content of lemma 3.10. Recall that the Gaussian function was defined as gamma of x equals e to the power minus pi times the norm of x squared. We already observed earlier on the lectures that the Gaussian function is a Schwarz function, and now lemma 3.10 claims that the Fourier transform of the Gaussian is again the Gaussian. Let us also record that since the Gaussian function is radially symmetric, the tilde version of the Gaussian function equals the Gaussian function itself. So hat gamma equals gamma and also tilde gamma equals gamma. From these observations, we see that at least the Gaussian function satisfies the Fourier inversion formula. Gamma equals hat tilde hat of gamma. Of course, one could pile any number of hats and tildes on top of gamma and one would always end up with the same old Gaussian. Things are not quite that straightforward for more general Schwarz functions. Let us then prove lemma 3.10. We already mentioned earlier on the lectures and left it as an exercise to verify that the Gaussian function is a Schwarz function. It remains to check the formula hat gamma equals gamma. The first step is to reduce this claim to the case of ambient dimension d equals 1. This is based on the fact that the exponential function turns sums into products. If x equals x1, x2 through to xd is a vector in Rd, then e to the power minus pi times the norm of x squared equals the product of the factors e to the power minus pi xj squared. This observation allows us to rewrite the Fourier transform of gamma as a product of one-dimensional integrals. First, by definition, hat gamma at xi equals the integral of gamma at x times e to the power minus 2 pi I x dot xi dx. This equals the integral of e to the power minus pi times the norm of x squared times e to the power minus 2 pi I times the sum of xj times xij dx. Using the previous formula for e to the power minus pi times the norm of x squared and Fubini's theorem, this d-dimensional integral can be decomposed as the product of d one-dimensional integrals of the form integral of e to the power minus pi xj squared minus 2 pi I xj xi j dxj. Now we observe that each of these one-dimensional integrals equals the Fourier transform of the one-dimensional Gaussian evaluated at xi j. So once we manage to prove that the Fourier transform of the one-dimensional Gaussian at xi equals e to the power minus pi times xi squared for any real number xi, we will see that the Fourier transform of the d-dimensional Gaussian at xi equals the product of the factors e to the power minus pi xi j squared. Finally, using once again that the product of exponentials is the exponential of a sum, this product equals the d-dimensional Gaussian evaluated at xi. And this is what the lemma claims. It therefore remains to prove the lemma for the one-dimensional Gaussian. There are at least two approaches. One of them needs a bit of complex analysis, and the other one needs a bit of knowledge in differential equations. The complex analysis approach is taken in Mikko Salo's lecture notes, so here we will take the route via differential equations. We are claiming that two smooth functions, namely the Gaussian and its Fourier transform, are the same function. To see this, we will verify that both functions satisfy the following ordinary differential equation. Y prime at xi equals minus 2 pi xi times y at xi. As the initial value condition, we require that y at 0 equals 1. Once we manage to verify that both the Gaussian and its Fourier transform satisfy this differential equation with the same initial value at 0, it follows from the Picard-Lindelöf existence and uniqueness theorem that gamma and hat gamma are equal on the whole real line. Verifying that the Gaussian e to the power minus pi xi squared itself satisfies this differential equation is trivial. Moreover, we will take for granted here that the Fourier transform of the Gaussian satisfies the correct initial value condition. In other words, the Fourier transform of gamma evaluated at 0, which equals the integral of e to the power minus pi times x squared dx, equals 1. If you have never seen this calculation, then you may wish to check out the Wikipedia article with the title Gaussian integral, which contains all the details. What remains to be done is to check that the Fourier transform of the Gaussian satisfies the correct differential equation, namely that the xi derivative of hat gamma at xi equals minus 2 pi xi times hat gamma at xi. To prove this, we start with the left-hand side. Writing out the definition of the Fourier transform and differentiating under the integral sign, the xi derivative of hat gamma at xi equals the integral of minus 2 pi I x times e to the power minus pi times x squared minus 2 pi I x xi dx. Here we recognize that the factor minus 2 pi x times e to the power minus pi x squared equals the x derivative of the Gaussian e to the power minus pi x squared. Now we have written the xi derivative of hat gamma at xi as an integral of a product of two functions, one of which is a derivative. These functions might be denoted u prime and v. Whenever you see such an integral, you should try integrating by parts. We do exactly that, and we find that the previous integral equals a certain boundary term, namely u times v evaluated at infinity minus u times v evaluated at minus infinity, minus the integral over r of u times v prime. As you may recall, u of x was simply the Gaussian function evaluated at x, and v at x was e to the power minus 2 pi I x times xi. Hence, v prime at x equals minus 2 pi I xi times e to the power minus 2 pi I x xi. All of this looks a little complicated, but first of all, the boundary term vanishes completely because the Gaussian function u vanishes at both infinity and minus infinity. Also, the second integral can be simplified a bit by cancelling out the product of two factors of I, which yields an additional minus sign. The final result is minus 2 pi xi times the integral of e to the power minus pi x squared minus 2 pi I x xi d xi. And this finally equals minus 2 pi xi times the Fourier transform of the Gaussian evaluated at xi. This last expression is the one we were after, and now we have shown that the Fourier transform of the Gaussian satisfies the correct differential equation. This completes the proof of lemma 3.10. We are then almost ready to prove the Fourier inversion formula stated in Theorem 3.9. We still recall some technical tools we have already seen or used before. The first one is the duality formula for L1 functions f and g, which stated that the integral of hat f times g equals the integral of f times hat g. The second technical tool is lemma 3.11 about approximate identities, which we have already seen in the 2-pi periodic setting. Let psi delta be a collection of continuous functions on Rd indexed by a positive parameter delta. This collection is called an approximate identity if it satisfies the following axioms A1 through to A3. The axiom A1 states that the integral over Rd of each function psi delta is equal to 1. The axiom A2 states that the L1 norms of the functions psi delta are uniformly bounded, independent of the value of the parameter delta. Note that if the functions psi delta happen to be non-negative, as will be the case below, this already follows automatically from axiom A1. The final axiom A3 states that the functions psi delta converge uniformly to 0 outside any fixed neighborhood of the origin, as delta tends to 0. More precisely, if epsilon is a fixed positive number, then the restrictions of the functions psi delta outside the ball b0 epsilon converge uniformly to 0 as delta tends to 0. If these three axioms are satisfied, then the convolutions of fairly general functions with the approximate identity have nice properties. For example, if phi is an L-infinity function which also happens to be continuous, then phi convolved with psi delta converges pointwise to phi as delta tends to 0. This is the part of the lemma which we will need very soon. A second useful fact concerns the convolutions of the approximate identity with LP functions, when the exponent p is finite. If f is such a function, then the convolution of f with psi delta converges to f in the LP norm. We are then ready to prove the Fourier inversion formula for Schwarz functions. We start by noticing that the Gaussian function gamma can be used to construct an approximate identity. Namely, for a positive parameter delta, define the function gamma delta by setting gamma delta of x equals delta to the power minus d times gamma evaluated at x divided by delta. Then every gamma delta is a non-negative function with integral 1. It is also not difficult to check that the restrictions of the functions gamma delta outside any fixed neighborhood of the origin converge uniformly to 0 as delta tends to 0. We leave this as an exercise. Therefore, the family of the functions gamma delta satisfies all of the axioms A1 through to A3. Now, to prove the Fourier inversion formula for Schwarz functions, fix a Schwarz function phi, and also a vector x in Rd. We use the previous lemma on approximate identities to express phi of x as the limit as delta tends to 0 of the convolutions phi convolved with gamma delta at x. We next spell out that this convolution equals the integral of phi at y times gamma delta at y minus x dx. To be accurate, here we already replaced gamma delta at x minus y by gamma delta at y minus x using the radial symmetry of the Gaussian function. Next, we simply spell out the definition of the function gamma delta. We find an integral of phi at y times delta to the power minus d times the Gaussian evaluated at y minus x divided by delta. Finally, we use lemma 3.10, which stated that the Gaussian agrees with its own Fourier transform. So the function gamma in the integral can be replaced by the function hat gamma. To proceed from here, we need to recognize that the function y maps to delta to the power minus d times hat gamma evaluated at y minus x divided by delta equals the Fourier transform of a certain other Schwarz function evaluated at y. This Schwarz function is the function gamma superindex x delta, whose value at xi equals e to the power 2 pi I xi.x times the Gaussian function evaluated at delta times xi. With this notation, the Fourier transform of gamma superindex x delta at y equals delta to the power minus d times the Fourier transform of gamma evaluated at y minus x divided by delta. Checking this equation carefully requires a bit of effort, but one probably needs to do it oneself to get really convinced. It is based on using multiple formulas from proposition 3.8, and we will not even attempt to show more details here. With this formula in hand, we may continue from where we left off. Recall that phi of x equals the limit as delta tends to 0 of the integral phi at y times delta to the power minus d times hat gamma evaluated at y minus x divided by delta dy. As we just observed, this latter quantity can be expressed as the Fourier transform of gamma superindex x delta evaluated at y. Now we are looking at an integral of one L1 function times the Fourier transform of another L1 function. And we may use the duality formula. As a consequence, the integral above equals the integral of hat phi at xi times gamma superindex x delta at xi dxi. Next, one needs to recall the definition of the function gamma superindex x delta. Evaluated at xi, this equals e to the power 2 pi I x dot xi times the Gaussian evaluated at delta times xi. If one now compares the left and right hand sides of the long formula above, one can already recognize the Fourier inversion formula. The only thing which is not yet right is the factor gamma evaluated at delta times xi. However, as delta tends to 0, this factor tends to the value of the Gaussian at the origin, which is equal to 1. Finally, it follows from the dominated convergence theorem that as delta tends to 0, the integral tends to the correct right-hand side of the Fourier inversion formula, namely the integral of hat phi at xi times e to the power 2 pi I x dot xi dxi. We have now shown that phi of x equals the integral of hat phi at xi times e to the power 2 pi I x dot xi dxi. And this completes the proof of the Fourier inversion formula for Schwarz functions. We conclude the lecture by pointing out that one can extract a bit more information from the proof above. Theorem 3.12 is often known as the Fourier inversion formula for L1 functions. Let f be an L1 function and assume that also the Fourier transform of f is an L1 function. This is a very strong additional assumption, and it is definitely not true for general L1 functions. Under this assumption, f of x equals, for Lebesgue almost every x, the integral of f hat at xi times e to the power 2 pi I xi.x dxi. Since we assume that hat of f is an L1 function, the right-hand side of this equation defines a continuous function on Rd. In particular, f coincides almost everywhere with a continuous function. We leave the proof of Theorem 3.12 as an exercise. The idea is to have a look into the proof of the Fourier inversion formula for Schwarz functions and think carefully whether Schwarz function assumption can be relaxed. On the next lecture, we will use the Fourier inversion formula to prove the Plancherel and Parseval identities for the Fourier transform. This will allow us to define, finally, the Fourier transforms for L2 functions. This concludes lecture number 13 on the course Introduction to Fourier Analysis.